So previously we've looked at weighted data driven approach, the nearest neighbor classifier, then we did the linear classifier, and we saw that there are these learnable parameters, the W's, and we now want to find good values for W. So for the linear classifier, you can actually find the so-called closed form solution. So because it's a convex function, we can get to the correct minima in the loss function like directly. But let's not worry about that. Let's just focus on neural networks. Neural networks, we cannot do it, so we don't want to talk about it. We're going to talk about a more general approach, the so-called gradient descent approach. And it's a very simple approach. Let's look at it how. So let's say, this is our loss curve, right? So we know that loss is a function of, your, let's say, so we already know that loss is, let's say, your cross entropy in this case, and cross entropy is a function of your output and targets, and we know that the output is a function of your input and weights. So in some sense, we can write that your loss is a function of your, let's say, inputs, your weights, your targets. Yes. Now we cannot change the inputs, we cannot change the targets, because inputs are what they are and we have corresponding targets for those inputs. But now we want to find, what are good values for W. And now let's think of like a single value for W, right? Let's imagine on the x-axis we have just one parameter W, a scalar, right? Usually this is not the case, but this is to kind of explain. And now let's think of, our loss looking something like this. Again, loss will look very different, but let's suppose it's a very nice looking convex function. And now let's say we start with some random initialization of W equals W naught, and let's say our W naught happens to be here, right? Now we want to get to here because on the y-axis we have our loss and our goal is to minimize the loss. So how would you do that? Yeah, so a very simple approach is to find the derivative of the loss at this point. What is the derivative in 1D? It is just a tangent to this curve at this point, right? And once we find the tangent, we can take a small step in the negative direction of the tangent. The tangent is usually in this direction, so we can find a small step in this direction. And then we do that a little bit more. We then, take one step, we're here, and so we get to here, let's say W1, and then we find the tangent at this location, and we then take a small step in this direction, and so on. So let me rub this and write it a little bit neatly. Yeah. So what we were saying is, so we found our W naught to be here, then we found, so this is our W naught, then we took a small step and we came to W1, and so on. Now if we were to write it mathematically, what would it look like? We would say W1 equals, let's say, W naught minus our derivative of loss with respect to W, right? And a small step of size lambda. So lambda is your step size. In our neural network lingo, we will call it the learning rate. But all that later, we'll talk about it when we look at backprop. But let us look at just this simple gradient descent, and I think it will get crystal clear when you actually implement it, because all you will do is you will actually find this quantity and then you would iteratively do a loop, and you would reduce this dou L by dou W from your original W and keep doing that until convergence. So the concept is very simple. If we now visualize it in, say, 2D, because we actually our weights will be much bigger, but we cannot visualize it. But let's say in 2D we have, these two axes are W1 and W2. So now our W is not just a single number, but two numbers, W1 and W2. And this f of x is essentially our loss. And what do we want to do? We want to find the minimum point of the loss. So ideally we want to get till here, right? And let's say this is our W naught, right? So W naught is essentially let's say W1 naught and W2 naught. Yeah, and our goal is to get till here, but what will happen with gradient descent is we will get to the closest minima, and that is fine. But how do we get there? So now in 2 dimensions you do partial derivatives instead of, and partial derivative is nothing, it's just the derivative of loss with respect to W1 and W2. So when we differentiate it with respect to W1, we assume W2 to be constant, and similarly when we differentiate it with W2, we assume W1 to be constant. And then for each parameter individually, so Wi, so if I is equal to 1, it becomes W1, we take a step in that negative direction of W1. So lambda times d loss of W1 by d of W1. Yes. So and we then do the same for W2. But remember, so when we do this, I mean, we'll look at it in a bit more detail when we do backprop next week, but in 2 dimensions or higher dimensions, this tangent is then called like a gradient, right? So the gradient is essentially this quantity, and we then use the gradient and we go in the negative direction of the gradient. We take a small step in the negative direction of the gradient. So from there we might come here, then we might come here, and finally after a few steps we might come here. But now this is a local minima and we get stuck in that local minima, and that is okay for now, right? So we are finding a local minima and we want to get till there in the landscape, in the loss landscape, where the parameterization is through our weights, the W1 and W2 in this case. Now what we just learned is, we want to find good values of W, and we'll do this again in the next week. But suppose you were to write the code for it, which is again a homework assignment, and your TAs will help you with that. But what we need to do is until convergence, yeah, this is why we have while true, you get your x and y and you find your derivative of your loss with respect to your output. You back propagate through your model and then you update the weight, right? But this is using the backprop which we learn in week 1. So instead what we can write is a slightly modified code, right? While true, what we do is we find the loss at the current point, and then we find the derivative of the loss with respect to W, and we take a step in this direction, in the direction of say W minus lambda times derivative of loss, right? Lambda times, oops, so minus lambda times derivative of loss with respect to W, component wise. Yes, and backward is nothing but just doing this quantity, but this will get really clear in our first week. For now, what you need to remember is just what we discussed. What we want to do is we want to minimize the loss, and the way to minimize the loss is by starting at some W. In this case we started at W0 here, in this case we started at W0, but here W0 was a vector, and usually this vector will be much larger, and then we find like a plane, or in this case a tangent, and we take a step in the negative direction of the tangent, and that's it. We just do this in a loop, and eventually we get to the nice minima that we are looking for, and that is how we have optimized our loss function, and those are our final values of the weights. We now are done with optimization. We take these weights and then we use that as our model, and this is something that we will do in the so-called inference. So this is the training step where we find good values of W. Once we have found good values of W, we are done with training. We then remember those values and then we use it for inference, and we will also do that as part of our assignment, and it's very simple.